There we go. Good. Looks like we're seeing all this. All right. So what we're going to do, as I said, we're going to get into decimals quite a bit. So 1.3 in this book, they start out with talking about functions and whether they're even or odd. Okay. I'm not real big on the even or odd idea, but I'll just kind of go ahead and give you a little bit. So we're going to talk more about functions and their graphs. And the first thing they're going to talk about is even and odd. Okay. So the book defines, or the text defines, even function as this. So it says a function is even if it takes f of negative x is the same as f of x. So what exactly does that mean? Well, it means that it doesn't matter whether you put a positive number in there or a negative number into the function. You're going to get the same thing. So the first thing that comes to mind might be absolute value. Okay, so if we have f of x equals the absolute value of x, we know that if you take positive numbers, they stay positive, right? The absolute value of a negative number is also positive. So when I teach absolute values, it's just like distance. Okay, so if I go from Portland to Rock Creek, right, or Rock Creek to Portland, it's still the same distance. It is in an opposite direction, but it's still the same distance. Okay, so absolute value is a lot like distance, and that never can be negative. It has to be a positive value. All right, so you can go in a different direction, but it's always going to be a positive. All right, so the absolute value of a negative 5 is 5, and the absolute value of 5 is 5. So we would say that's an even function because negative x and x are giving me the same y value. So any function that looks like that is going to be even. And the real way to test it out is to just check to see if it's symmetric over the y-axis. So what does that mean? So that means if you cut it in half in the y-axis, okay, it's going to fold over. So that this graph here, right, will fold over this y-axis and be the same as what's over on this side. Okay, they'll be the same thing. It's symmetric. Okay, that's what that means. So you can reflect it over. Now, an odd function is sort of the same thing, except it goes like this. Okay, so it says, hey, if I take a negative value for an x, then I get the opposite of what I have when I take a positive value of it. Okay, so if I take, say, f of 1, okay, then I'm going to get the same thing. I'm going to get the opposite, sorry, if I take the f of negative 1. So the f of negative 1, right, is just going to be the opposite of f of 1. That's basically what it's saying there. So what that looks like is a little different. So it's kind of like this. All right. And we had a graph kind of like that. I drew one like that yesterday or on Monday. So that takes this one and it's kind of rotated around the origin 180 degrees. So if you can take and visually rotate that 180 degrees, all right, so it's rotated 180 degrees, then that's an odd function. So you should be able to kind of tell by looking at their graphs whether they're odd or even. Even is pretty easy to see. odd, a little harder to see. They have some nice little graphs in the book. Okay. They also have a test. All right. And they say, all right, so is there a surefire way of doing it? So let's say you have f of x equals x squared plus 5. And it says, all right, we see that that's x squared plus 5 for f of x, but what is it when x is a negative? So we would go like this. Okay, and then we're going to go like this. And of course, that's just going to be an x squared because a negative times a negative is a positive. And sure enough, they're the same thing. So then we would say that this is even. But again, you could just graph it, right? And you could see that that's going to be a nice little parabola U shape. And if it's symmetric over the y-axis. So you would do the same thing. So let's try another one here. We'll say x cubed plus 1. All right, so now let's check see if it's even. All right, well then that means I'd have to get the same thing. So if I put a negative x in there, okay, but unfortunately if I take a negative x to the third power, that's a negative times a negative, which is positive times another negative is actually negative. So I get this, and they are not the same, so this is not even. All right, so then let's check to see if it's odd. All right, so that means that if I put a negative x inside here, so I'm doing this exact same thing, all right, so I already know what I'm going to get, then is it equal to the same as this? Okay, well, let's break this down. So that means I take f of x, which is x cubed plus 1, all right, and I would put a negative out in front. Sure enough, I get negative x cubed, but I also get negative 1. So since I get a negative 1 here, and not a plus 1, then it doesn't work, okay? Because right here, when I take this, I get plus 1, whereas when I take the negative, I get a negative 1. So that doesn't work. So it's not odd either. Okay, they have to be identical, right? And it's hard to come up with those functions, right? But they are, there are some there where that's going to work out. Okay, but
so is there a definition since that one's not even or odd?
No, it's just not even or odd. It's just a regular old function. Okay, so you're kind of better off to just graph them, all right? To be honest with you on those. So what I'm going to do now is let's go explore some things in Desmos. Okay, so I'm going to go back to here. And let me get the stop here. Let me see if I can, a new share, do this. I want to share this out. I'm going to get rid of these guys. Now I'm going to wait. I want to make sure you're kind of there. Okay, so we're going to put some functions in here, and then we're going to talk about them. I just want to make sure I'm in a... Okay, good. All right. So let's put these in. I'm just going to go y equals, and I'm going to start with a simple one here. I'm just going to go parentheses x plus 1 parentheses x minus 1. So I'm going to put that in there, okay? So on these functions, what they're going to start talking about, first of all, is if they're increasing or decreasing, okay? Now, This type of idea has caused students problems. And at first it might seem fairly straightforward, but I've seen it cause problems. So when you are talking about increasing and decreasing, first of all, you're going to go from left to right. Okay, so you're going to start on the left-hand part over here. I don't know if you can see. Let me see if I can do a little annotation here. All right, there we go. So we're going to go left to right. So we're going to start here, and we're going to see what this function's doing. All right. So now I want to stop this. So here I'm going to hope, oh, there it is. So I'm going x to right on the x-axis. So I'm not looking at the x points, but I'm looking at the y points. And I see that the y points are getting smaller, so they're decreasing. Okay, so we say that this function is decreasing going left to right. So we would say from negative, I'm going to go over here, from negative infinity to some point, this function is decreasing. All right, so I'm using interval notation where the parenthesis means that it does not include that number. And you can't include infinity because it's infinity. All right, so you can't include it, so you put a parenthesis there. But at some point, all right, this thing is flat. All right, it's not increasing or decreasing. They say that it's on a constant. And that's going to be right down here at the bottom. Okay, so at 0, nothing's happening there. It's just flat. And then after that, okay, it starts to increase. Okay, remember we're going left to right, so it starts to increase. So then what we're going to say here is that from negative infinity to 0, okay, with a parenthesis, because it doesn't include 0, that it's decreasing. But from 0 to positive infinity, it's increasing. So you can think of it as falling and rising. Okay, falling is decreasing, rising is increasing. You're always going to go left to right. Always go left to right. So that's how we would write that. You don't have to worry about saying, oh, at 0 it's constant. Okay, we're not going to worry about that. So right now, that's all we're talking about is this is called intervals of increasing or decreasing. Okay. So I'm going to clear this off. And let's take this one out. Oops, I got to exit this. Let's take this out, and I'm going to put another one in. And if you have questions at any time, feel free to ask away there. All right. I'm going to put a number out in front of this, I think. Let's make it 2 maybe. That's a little better. Okay. All right, so again here what we have, we're going left to right. All right, we're going left to right. So I see that this function is increasing. It hits this top point right there. And now it's no longer increasing or decreasing. So it's kind of like a roller coaster. So it goes up, and you hit that exact point where that car that you're in might be just that instant. It's just sitting there. And then, boom, it falls, right? So up, 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 sits, and boom, down, right? And then it hits a bottom here where it's going, and there's one point in the bottom where it transitions from going down to up, so it might even have nothing going on there, and then it goes back up, 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 up. So we have increasing, decreasing, increasing. So how do we say that? Well, let's do that here. Okay. think I'm still in the draw mode. I'm not sure. There we go. So I'm going to say that increasing. So I'm going to put increase here. Again, I'm going to start with a parenthesis, so negative infinity, right? Always go left to right. Negative infinity to, what was that point? Oh, man. To negative 0.786. Sorry about that mess there. Oops. Okay, that's increasing. All right. Now it's increasing again from this point on up. All right. So I could go here and tap on that. Oh, it's 2.12. Okay. So now I'm going to go here. I'm going to say from 2.12 to positive infinity, it's increasing. Notice how I'm putting parentheses and not brackets, because at that 2.12, or approximately, because Desmos approximates everything, it's flat. Nothing's happening there, okay? Now I'm going to say, when does it decrease? Well, it's going to decrease from those 2 points, the negative 0.786 and the 2.12. And everything else, that's how it works. So, up, increasing, down, decreasing, back up. Any questions on that?
Do you separate those numbers in the parentheses with a comma, or do you just leave like space between them?
It's always been my feeling that if you put a comma in there, then you could be talking about a point rather than an interval. Does that make sense?
Sure, so do you just put like a space between them?
Mm-hmm. Just put a space in there between them. Okay, so that's pretty much intervals, increasing, decreasing. Okay, always go left or right, and that's what you're looking for. All right. Let's see. Let's go like this. Okay. The other thing that we want to take a look at is max and mins. So I think what I'm going to do actually is go back to here. I think this is what I'm sharing. I lost it. Oh yeah, nope. Hold it. I thought I was. There we go. All right, so let me wrap that up real quick here. There we go. So if I draw a graph, all right, like this. Okay, I'm just going to put a point right there. We'll call that 1. And we'll put a point right there. We'll call it 3. All right, so I would say increasing negative infinity to 1. I'm only looking at the x coordinates, not the y's. And from 3 to positive infinity. Okay, and then decreasing from 1 to 3. That's how we do intervals of increasing, decreasing. Now, the other thing that we're going to talk about is maximum and minimum points. Okay, and again, we're going to use Desmos. It's so easy to get those. So your maximum and minimum points are points, first of all. All right, and most of the time I'm not real sticky about things, or really particular, I guess. But this thing I kind of am, because these are points. Okay, so oftentimes I get somebody say, the maximum point is 10. Well, wait a minute, it's a point. When is it 10? All right, you got to tell me more than just a number. Okay, I like to know when that maximum minimum point occurs. So make sure you write it as a point. There's 2 types. Okay, there is absolute and local. That's what they use here. So there's local points and there's absolute points. Now the difference is that local is within an interval. Okay? And absolute is not. It's throughout the whole thing. All right? Okay, so what do I mean by that? So let's say that I sketch a graph down here. And I'm just going to keep drawing these 30 degrees because I kind of like them. There they are. All right, so then we say that this graph has local maximum minimum points, okay? And the maximum point is right there. That is the maximum. Now, why is that a local point? Well, because if I cut this off, let's say I cut this graph off here to here, then that is the highest point on that graph. Okay. Now, maximum and minimum points usually occur at a bend. Okay, that's why, remember what we were just talking about? I was saying, well, we don't worry about when that increasing, decreasing, or we don't worry about when it's constant or it's flat, because that's a maximum or minimum point, usually. Okay, it's rare that it's not. So that would be a local maximum. Okay, local maximum. Here, if I go down here, then this would obviously be a minimum. Okay, and we would say again that that's local. Now, the reason again for that is because this function continues to go in either direction. So I could come down here and say, you know what, that's more of a minimum than this one is. So it has to be local. It can't be absolute, because absolute means that there is no point lower than that one, or there is no point higher. So let's look at something like that. So let's say we got a graph here, okay, and I'm just going to make sort of a W sort of graph, or an M, sorry. So on this particular case, this is a maximum, but it's an absolute maximum because there's no point higher than that. Okay, we're assuming that this graph is going to continually go down on both ends. All right, so that's an absolute maximum, whereas this is a minimum, but it's local because this graph is continuing to decrease. Okay, it's continuing to go down. Here, that's a maximum, but again, it's a local one because obviously this one's higher. So that's how maximum minimum points work. So let's graph some in Desmos and take a look at it. All right. So let's see, I'm going to go like this, here, and here, and here. I'm just going to get rid of these, put in some new ones. So I'm going to go y equals 0.2, and actually let's put it, we'll go like this, x minus 1, x minus 2, let's go with that, x plus 1, okay. All right, and we'll leave it like that. Okay. So here we are, right? Increasing, but at some point, see, I just tap right where I think it is. Now I have to be careful because these 2 points are pretty close together. Hopefully you see what I'm talking about. This one is not a maximum. This one is. See, it's how the y is just a hair bigger. Okay? That 0,4 is just a y-intercept, and Desmos just gives them to you, even though not of a whole lot of importance here. So this one up here that I'm talking about right here, let me annotate on it. I'm getting tired of purple. Let's do some orange, or I don't know. I don't want to do red because that's what it is. Green. This, is that local or is that maximum? Is it local or absolute?
Local.
Yeah, it's local. Somebody asked about the union symbol for increasing. If you wanted to put a union between the two intervals, you could. That wouldn't be incorrect at all. It's just that's up to you. Okay. Yeah, so that's local. Okay. Then what about right here? What's that going to be? Local min, right? So you got to figure. Yeah, that's local. Okay. So in Desmos, it's real simple because all you do is tap right where you think it is. Okay, and it will tell you. All right. But remember, write down the whole point. So when you're telling me, hey, this is the local, and if I say, hey, what are the local mins and local maxes? For the local max, you'll say negative 0.215 and 0.42 or something like that. I don't care how far you carry it out. If you go negative 0.21, that's fine, and 0.42. And then the other one would be 1.5 and negative 0.12. So make sure that you're kind of writing it as a point. Okay. So now let's go ahead and let me clear that out of there. All right. And let me come back up to this. Oh, you bugger. Let me come back up to this. Oh, I didn't. Gosh dang it. There we go. And I'm going to throw another parenthesis in there. We'll just leave. No, let's go like this. There we go. Oh, that's better. Okay. So now we have this one, right? So then here, decreasing. See, I'm bringing that into decreasing, increasing, decreasing, increasing. So let's find our maximum, minimum points. There's one. There's one. There's one. See, here I got to be careful because they're close. All right. So where's my locals?
Negative 0.07, 1.207 is your local maximum.
Yep. Okay, good.
2.254 and or 2.59 and 0.
What's that one? A minimum? Is it absolute or local?
It's a local minimum.
Which one's a local minimum?
Absolute minimum. Both of the minimums would be absolutes, right?
Okay, that's a good question. So that's what we got to sort out, right? So which one is now? They both can't be, all right. Now there could be a situation where I'll show you where they both could be, but in this case, no. One of them's absolute, one of them's local. Which one's absolute?
The one on the left-hand side.
The one on the left-hand side, right? Because it's the furthest down. There's nothing smaller than this. Okay, this graph doesn't go down any further. All right, so that's an absolute. This one would be a local. Okay, this one would be a local. So let me see if I can show you. All right, now here, I would agree with you. Those have to be absolutes because they're the lowest points. Okay, so there's nothing lower than that. So then those would be absolutes. Okay.
And you would need to list both of those for the correct answer then, right?
Yeah, because they're different. There's different points, right? Yeah. And then what about the 0.8? What's that one?
That's the local
max.
Local max, right? Again, there's numbers higher than that. Okay, so that's what we got to be careful of. I want to see if I can do some more with this. Let's see. Let me cut it between -3 and 3. Okay, and let me make this. All right. So there it goes. It stops. Okay, so here, all right. Now that says it's undefined. Let me change it. Delete that. Put this. Delete this and put this. There we go. Okay. This one's a little tricky. All right. So then this becomes one of those points. Okay. These ending points, now that this function ends, right, and it's not bending, this becomes a point. So then this one here, this 3 and 8.8, what would that be? Would that be a maximum or a minimum?
Maximum.
That's a maximum, right? Is it absolute or is it local?
Absolute.
That's right. That's the highest you can go, right? Here's another one. What's that?
The local max.
Okay, what about this? Local max,
local.
right? What is this one?
Absolute. Absolute.
Min, good. And what about this one? Local min. Okay, so you're kind of catching it. All right, good. Good, good, good. And all you got to do is graph them, okay? So you don't worry about, or you don't have to do any other things to worry about anything else there, okay? I guess we talked about zeros before, so I don't think there's anything else in here. It's all just about maximum minimums. I think it'll be okay. It talks about, I don't know if, did I give any of those? Let me see. I did. Okay. All right, let me do one more thing here with this section. Go like this. Go like this, I guess. Okay. They're going to talk about the average rate of change. So this is kind of building some foundations for calculus for those of you who have to move on to that. All right. Let's say that this is 3, and I want to say this is 5. Okay. So if they say they want to know the average rate of change from 3 to 5, and they just go 2, 5. Then what we're going to do is we're going to come down here to 3, and I'm going to put a point there. Go to 5, put a point there. And then I'm going to connect that with a line, kind of. Okay? Visually, anyway. And the average rate of change is just the slope of that line. Between these 2 points. Okay? So that would be between 3 and whatever that y coordinate is, I'll call it y1, and 5 and whatever that y coordinate is, and call it y2. So then let me put some numbers on here so that we got something to go with. So here I'll call this -2, and of course that one's 0. So then if I want to find the average rate of change, all right, I'm going to find a slope. And you should know that's how you find slope. All right, so then we would go, okay, I'm just going to pick -2 minus 0 over 3 minus 5. And I'm going to see what that slope is. So that'd be -2 over -2. How about that? Which is just 1. So that would be the average rate of change. All right, so you're just taking those 2 points and finding the slope of the line that goes through there. Any questions on that stuff? Okay. Let's see here. All right, let's do this. Let's take a look at 1.4. 1.4 calls it a library of functions and then piecewise functions. Well, let's just start with a library of functions. Okay. So what we're going to do is do some stuff on Desmos. So I like to call this a toolbox of functions. Okay, so it's kind of got all kinds of functions in this box, and I need to know certain things about them. What is it that I'm interested in? I'm interested in the shape of the graph. I'm also interested in the domain and the range. Okay? Those are the things that I'm interested in. These 3 things. Shape of the graph, the domain, and the range. So we're going to explore some of these in Desmos. So let's go there. I'm going to get rid of that one. All right. Now, first of all, I'm going to start with a line. Okay? I put an A in there. All right? And now I'm going to put an X. And it asks me if I want to add a slider. And I want to click on the A and say yes. All right? So hopefully I'm not going too fast and you're able to get into Desmos and see what I did there. So what this does is it allows us to change the A value, okay? And we know that this is a line, all right? And we've dealt with lines before, so we're pretty comfortable with those, all right? Obviously the shape is linear. What's the domain?
All real
numbers.
Good. What's the range?
All real numbers.
All real numbers, okay? So if you're keeping a list of these functions, then what you would write down is I'm going to put down a linear y equals x, and I can put an A there if I want. Domain, all real. Range, all real. All right. And obviously the graph is a linear. Okay. So I know that. So that's the first thing I got in the old toolbox. So now what I'm going to do is go to the next set of functions. All right. So I'm going to go back into Desmos here. And I'll come back to this screen. Oops, right there. Okay, and I'm going to put an x squared on there. But this time, what I'm going to do is I'm going to actually get rid of that A. And I'm going to go x to the, and I'm going to put an n in there. And this time I'm going to add a slider n. I'm going to get rid of this, and I'm going to change this. So I tapped. Let me go back and show you what I did, because I feel like I'm going too fast. I tapped on this negative 10. Okay, first I don't want that anymore. I tap on this negative 10, and I can change it to whatever I want. So I'm going to change it to 1. And now I'm going to come to this, and I'm going to change that one to 6. And I'm going to step it by 1. So what I'm doing is I'm telling Desmos, I'm saying, hey, I want you to take this n value, and I want you to go 1, 2, 3, 4, 5, 6 for me. Okay? That's what I'm telling Desmos to do. I don't want any fractions or decimals in there. I just want nice whole numbers. 1, 2, 3, 4, 5, 6. Okay, so I'm going to stop there. So there's my line. All right? Now I'm going to slide this. I have that. Okay? So I'm going to ask you, there's the shape of my graph. What's the domain of range? What is it?
All real numbers.
All real numbers for both? Or just for the domain? Or just for the range?
For the domain.
Domain's all reals, good. What about the range?
0 to infinity.
0 to infinity. Okay, good. Good. All right. Now I'm going to switch this to 3. Now what's my domain?
All real numbers.
And the range?
All real numbers.
Good. Now I'm going to switch this to 4. What's the domain? All real numbers. Good. What's the range?
0 to infinity.
0 to infinity. Awesome. So, now let's go to 6. What's the domain?
All real.
What's the range?
0 to.
So then if I asked you, what do you think about y equals x to the 8th? What could you tell me about the domain and range?
Be all real numbers, and then 0 to infinity.
Sweet.
So all even numbers seem to be all real numbers, and then 0 to infinity.
And what kind of shapes are their graphs?
Parabola.
Parabola.
Yeah, they're sort of a U shape, right? Now, be aware, and we know that as soon as I do that, I'm transforming it, and I can make it change. All right? But in the most simplest and general example, that's what we got. Okay, so let's go back to the odds now. So there's 3, and there's 5. So what's going on with the odds?
The odds are just all real numbers.
Right.
Domain and range.
Okay, good. So here's what we got. Okay? These are called power functions. Power functions include a lot of different functions. Okay, so they include y equals x to the n. So when you're talking about domain, range, and shape of the graph, we're knowing we're getting different things. So when n is even, what's my domain going to be? All real, okay, good. And what's the range?
0 to.
0 to infinity, okay? So I'm going to go like this. I'm going to put a big bracket around that. It goes 0 to infinity, all right? And I know I'm going to get nice little U-shaped graphs, okay? But when n is odd, what's my domain? All real.
So is the range.
Okay, and what about the range?
Same. All real.
Same thing. So we see a pattern there, right? And then these ones, I don't know, they're kind of like a little swoosh or whatever you want to call that. That's what they're going to look like. Okay, those are power functions. Okay, those are power functions. Now, inside the power functions, okay, there's these things called root functions. All right, so now I'm going to take and we'll talk about those. All right, but they're really just power functions, but they're inside of the group of power functions, the family, if you want to think about it. So here we go back to Desmos again. And normally I'd probably have you spend some time exploring these, but I don't. We're getting a little on time here. So what I want to do is get rid of that, show you where the roots are. So we're going to go in here, we're going to go to functions. Oh, I should go y equals, in the functions, miscellaneous. And right down here, right above where it says loga, or right below the percent key, I'm going to put this. Okay? And it had an N there, so I'm going to put an N there. And then I'm going to put X inside. Now again, it asked me for a slider, so I'm going to say yes. And again, I want to change this, so I start with 1 to 6, and I'm stepping it by 1. Okay? All right. So now I'm going to play with this again. So there's a line. That's no big deal. Well, look, here's a 2. 3, 4, 5, 6. Okay, so tell me about your even roots. What's the domain? What's the range?
The domain is 0 to infinity. And the range is also 0 to infinity.
Okay. All right. I know you can't see what I'm writing, but we'll come back to this here. Okay, root functions. Y equals root n. Okay, so you said the domain was 0 to infinity. And you said the domain was, and you said the range was. Okay. All right, so now I'm going back to, oops, I'm going to go back, and I want to stay at Desmos here, but I don't know why I'm not showing it. There it is. Okay. What about when it's odd? Then what do we got going on?
All real
Yeah, all real numbers.
All real numbers for both.
In range, yeah.
Yep. Okay, good. Okay. So here's my root function. This is what I wrote down so far. Okay, so when n is odd, domain, all real numbers. Okay, I'm just going to go all real like that. You can write it in interval notation if you want. All real like that. Okay. I'm making little tiny sketches of these so I know what they look like. And the reason for this is because if you see these types of graphs, you should be able to say, oh, I think that's a root function. Oh, I think it's an even root function or an odd root function. Okay, so it's good that you know. These again are underneath that power function umbrella. Okay. So I'm looking through which ones that they have here in the book, and we've covered all of them except they talk about absolute value, but we kind of already did absolute value earlier when I was talking about that at the beginning. Okay. Right. And we can go and graph that in Desmos. I'll come back to that screen. Get rid of this. Get rid of this. Absolute value. There is a little key for that or button here. Y equals absolute value X. You can type ABS if you want. Whatever you want there. But you can use that. What's the domain and range of the absolute value function?
All real.
All real for domain?
0 to infinity.
0 to infinity. Okay. So here, this is going to be all real. And the range is 0 to infinity. Right? They also mentioned a reciprocal function, but that again is sort of underneath powers, and it's basically a simple rational one. Okay, so I'm just going to call it a rational. I don't want to get into these too much, okay, because again, they come back to them later. And we already said that we can't have a 0 here. So the domain of that would be anything but 0. So I'm just going to say x cannot be equal to 0. All right, and the same thing for the range. We can't have 0 in, and we can't have 0 out. All right, and that's simple of a rational. Again, they get a little more complicated later on. All right. I want to do one more, and then that'll be it. Okay. We won't get to piecewise, but that's okay. We can do those on Monday. All right. Here's what we're going to take a look at. I said we were going to do these, so I want to go ahead and do it. All right. So in the Desmos, I'm going to have you take a look at these. All right. So there are some functions in the, or y equals, in the functions in the miscellaneous part here of the functions button. Obviously they're functions because it says they are. So if you come down here to miscellaneous, I want you to go to the one that says seal and put an X there. All right. Then underneath that, we're going to go y equals functions. So underneath miscellaneous, and we're going to put floor. And then one more we're going to do is round. Now I don't want us to look at them all at one time, so we're just going to tap them and come back to them. Okay? So go ahead and let's take a couple minutes and mess around with these, explore, seal, floor, and round. Okay? Note the shapes of the graphs. Note the domain and ranges. Okay, so let's take a look at these. If I have my screen sharing, I really should turn it off unless we're doing something, because I want you guys to be able to look at your screens. But so here's seal. Tell me some things. I'm not very good about getting the chat up here. There it is. Tell me some things about this seal function. What's this doing?
Showing you the nearest integer.
Who said that? I mean, I'm sorry, I missed your name there.
That was Nathan.
Nathan, okay. Elaborate a little bit on that, Nathan. So, can you give me an example, like an x and a corresponding y value?
X and a corresponding y value.
Yeah.
Not really, to be honest.
Okay. So let's say I'm just going to go in here. All right. So right in here I have an x value of 0.54, and what's the corresponding y value for that? Anybody can answer, but 0.54. What's the corresponding y value?
Oh, 1.
Okay, it's 1. So then, all right. Let me check that out down here again. Let me go to 0.2. I can get pretty close to that. What's 0.2 going to give me?
Also, it's going to give you 1.
So now what is the seal function doing to the x's?
It's the nearest integer above it.
Okay, it's very good. So it's rounding upward, right? So seal is rounding up. Okay. All right. What about, let's check out floor. Okay. Tell me what floor is doing. What is floor doing?
Nearest integer below it.
Same thing.
Okay, so nearest integer below it. Okay, so it's rounding down. Now, it kind of makes sense to us because ceiling's obviously up and floor is obviously down. So that's why Desmos called them what they are. Seal is rounding up and floor is rounding down. Now, we had graphs like this, remember, with the eggs, and we debated, are these functions? And there was an issue with right here. So if I'm going across this here, let's say I start right down here at point, I'm trying to get right there, and right at 1, boom, it jumps up, right? So see how I can get really close and then it jumps up. All right, so these are functions because it gets really, see there's 1, 0, but then as soon as I come over here, it's just, all right, and Desmos is just rounding them. It's just really hard. You can see, boom, a little bit over 2. 2 is 2 and 2, so then it must be up here. All right, because if it was taking and rounding it down, 2 is gonna be 2, okay? But anything lower than 2, 1.99999 is gonna round down to 1. Okay, it's gonna round down to 1. Seal's the same thing. All right, if I tap on seal, see here, as soon as I get to 1, oh, it bounces back up. So 1's going to round up to 1, or excuse me, 1's going to be 1, but 1.1 or 1.0000001, boom, bounces up to 2. Okay, so that's why they're functions. It's just that one, I think somebody said nanosecond when we were doing the graph. That's kind of what's happening there. There is a point to where they're not. It looks like they're the same, but they aren't. Okay. Domain. How about the domain of these functions, seal and floor? What would we say?
Would it be all real numbers?
Yep. And what about the range?
All real numbers.
Everybody agree with that?
No, it would be a roster
It'd be like,
set.
yeah,
It's going to be what?
A roster set. I read that on the first page of the book.
A roster set.
A roster set, yeah.
Okay. I think I've heard that term, but I'd have to go back a long ways to remember what roster set is. We could just say it's
list out the y values because it doesn't include the values in the middle.
right. So then we could just say they're integers, right? Right. So -1, -2, -3, 0, 1, 2, 3. Okay, they would be your integers.
Is that the same for both the seal and the floor?
Let's look. There's seal, there's floor. So what do you think?
I think so. It would be the same.
It's going to be the same. Okay. Now, these are called step functions because obviously they make steps. And the one that is important is the floor. Okay. So let me go back to here and here. All right. So the floor function here, which we're going to call steps, okay, which is floor in Desmos, okay, is called the greatest integer function. And it's symbolized, they can symbolize it by using int of x, which stands for greatest integer. I've also seen bars used for that. I want to see if they use, I don't know. I've seen this type of notation. So it could be either one of these that they use for the greatest integer function. And basically, it does exactly what we're saying here, is that it goes like this, and it bounces up, and it bounces up, and it bounces up, and the same thing here, and here, and here. Okay, it's called the greatest integer function. And in reality, these are used in a lot of different places. Okay, you know, we talked about parking before, weights, anything that's in the step interval is going to be using greatest integer function. Okay. So I got through everything except for piecewises, which we'll look at on Monday. And that just means you can do every problem except for number 27. If you want to try it, you can. But we'll talk about piecewise functions on Monday. So I think you'll be okay with your stuff, though. And yeah, I think we'll be all right. So if you have questions on stuff, email me, ask me. I'm sticking around afterwards. Thanks for hanging in. There was a long night. I know I don't always intend it to be that way, but this one kind of, because we did the Desmo stuff, was. So apologize for that. Stop.